T1 prime. Now, let's apply Laplace transform to the second part of equation 1. I'm sorry to do that. We're not taking, let's call this 1A and this 1B. So, let's use the dictionary now on 1B. Question? Yes, question? No? So let's use the dictionary on 1B. Do we see anything in the dictionary? Okay, so let's Laplace transform 1B. What's the Laplace transform on the left-hand side of 1B?
To the third box or the third one?
What's the Laplace transform of y prime of t?
Well, that's
Y prime value is 1/6. Exactly. Add on to the of it.
is it prime?
Now, what about the right-hand side? Do we have anything in the dictionary that looks like the right-hand side? What do we have that looks like the right-hand side? The very last entry now. But let's understand now what we can do about the last entry. We have, so that is Laplace transform of x1 prime delayed. Now, if x1 prime at t minus 5 was 0 for t less than 5, and whatever it might be for t greater or equal to 5, whatever it is, then it would be the entry in the dictionary. What is that x1 prime of t minus 5 in reality? Well, let's say here is time, and let's say x1 prime of t is some orange curve. And remember, we have the implied assumption that it starts at 0. So x1 prime of t might be this guy. What's x1 prime of t minus 5? Is this shifted by 5? This involves what? When you shift x1 t, let's say this or something like that, for times up to minus 5, there is time 0. Here would be time, let's say, minus 5. So what would be x1 prime at t minus 5? You would be, well, you would be shifting this to the right by 5. So that would be, if this time is 5, it would be this curve. Well, this distance is always 5. Right? That's the actual x1 prime delayed by 5. If the orange line is x1 prime of t, the red line is x1 prime of t minus 5. For times 0 to 5, the red line is not 0. But again, this is an effect that completely disappears very, very soon. How long is this important? Really only for the first 5 minutes. So the implied assumption actually is expanded that not only x prime of 0 is 0, but also in the interval between minus d and 0, because that's the part that when shifted becomes something non-zero here, is also 0. If, here's what I'm saying, implied assumption is expanded to not only, I'm going to take the entire vector, all components equal 0, but also not only we are at the nominal steady state at time 0, we also at the nominal steady state d time before it. If that's the case, let me draw that curve with that assumption. With that IA, here's the picture we have. Here is t. Here is now, and let's put here time minus 5, 0, plus 5. Orange line is the actual x1 prime of t. So I put here, red line is x1 prime of t minus 5. Exactly. Okay? T minus 5 is the orange shifted by 5. So with the implied assumption, the orange line is 0 for that interval, and in this case, for the undelayed, I care in that interval because the actual delayed variable moves that to positive times. So that would be something, let's say, like that. And x1 prime delayed, shift this by 5 to the right, shifting this to the right, we get this, and then Felix.
Is that in general or just because it's 5 minutes in this case? So
In general would be with a delay, whatever is the delay. So the implied assumption would have it a hoparity with d. Let's see. Yeah, I write here for d. General delay.
So if it's an hour, it still applies?
Yeah. Again, I'm making my control system, first of all, delay of an hour would be highly unusual and not good, because delay really limits the performance of your controller. So you would do everything you can to decrease it so it's much, much shorter than that. If you're pumping somewhere, you would increase the pumping speed, okay? You really want to have a delay, if possible, only a few minutes.
Just make sure that's x prime of t equals 0, right?
Yes. X1 prime of tau, I use tau for that interval.
Is that the same thing as time?
No, this is actually the whole vector. Yeah, it's a time unit. I'm saying specific.
Oh.
I guess I could use t. I can use t. Okay. I think let's use t. It would be less confusing if I put t. Yeah, you're right. Yeah, let's change it to t. Anybody else? So do you understand the concept? You understand now with this concept, what is the red line? It's exactly what I have in the dictionary. So with the implied assumption, I'm getting now that the Laplace x1 prime of t minus 5 would be 0 for t less than 5. Okay? And whatever it is, for time greater or equal to 5. So now I can use a dictionary. important concept. Implied assumption is an important concept to understand what's behind transfer functions. Anybody? Doing okay, one?
I have no idea what's going on. I'm following you, but I'm just following the math. Like,
Well, the thing
I
is
don't
here
know,
concept,
it's
not
not-
math. This is concept. This is concept. The actual state variable may be whatever the curve is. Okay? That's the actual concentration. Right?
yeah.
I would be assuming that the actual concentration is equal to its nominal value, which means the deviation being 0. And you understand, deviation being 0 doesn't mean temperature being 0. It means temperature equals nominal temperature. We're never talking about 0 Kelvin temperatures here, okay? It's the deviation of the 0, which means the actual temperature is the nominal value. Okay? Sound okay? Deviation variable. So, what we're saying is, we are going to, I don't care what initially, what the time minus 5, 0, the actual x1 prime of t is. I'm going to replace it with 0. Why? Because very soon it won't matter.
I'm sorry, but why you say temperature? Wouldn't be supposed to be concentration?
No, it's an example of what that 0 means. I just want to make sure that you understand. I use temperature because obviously you can never have 0 Kelvin temperature. Just that you understand that. It's all deviation variables. So when I'm saying something is 0, I'm talking about deviation variable being 0. So actual variable is never 0. Clear, please? So what I'm saying, Juan, is that even though in reality the concentration was not equal to the nominal steady state for the 5 minutes before I started this analysis, whatever is my time zero.
Okay.
I will assume it's 0 because it doesn't make any difference. It will affect the first 5 minutes, it's an error for the first 5 minutes, but I'm not designing my controller for the first 5 minutes.
Okay.
I'm designing my controller for weeks, months, years.
Is that's like the e to the something?
Yes, exactly.
Oh, okay, got it.
Exactly. This is also something that disappears. Alright. So, with that implied assumption, I can now Laplace transform equation 1b. So, alright. So if we Laplace transform 1b with implied assumption. Now we get y prime bar equals, and now I have my x1 prime of t minus 5 is 0 for t less than 5. Okay? That's what the implied assumption makes it. For t greater than 5, it can be anything it wants. But my implied assumption makes it 0 for the first 5 minutes. And then I have the dictionary entry. So, what would my dictionary give me for the Laplace transform of this?
X1 prime bar, and then e to the minus 5s.
Excellent, Priya. Exactly. I have 0 for t less than 5, x1 prime of t minus 5 for t greater or equal to 5. So that h you see here is x1 prime. So as Brian said, h bar would be x1 prime bar, e to the minus my d is 5. Yes. Okay? Now I think I just erased equation 2 that I need. The equation I had right here had x1 prime bar. You have it in your notes, but I was wise enough to at least put the 2 in next to the last time. So Therefore, using equation 2, I replace x1 prime bar. I have, equals this. No. So I get y prime bar equals 0.0018 over s plus 0.111. Let me write the e to the minus 5s here, u prime bar. Okay, so this from 2. Okay? And instead of putting the e to the minus 5s at the bottom, I put that before the u prime bar. Plus 0.0111 over s plus 0.111 e to the minus 5s d1 prime bar. This is an input-output model now. X1 prime has completely disappeared. No initial conditions, nothing with it. And it's a direct relation between the measured output and the inputs, and you can see the Laplace transform of the manipulated input is involved in the Laplace transform of the disturbance. If you look at what is multiplying u prime bar, this quantity is multiplying u prime bar. What does this have? This has a bunch of numbers and s. So s here and I have s here. It's a function of s. Let's call this, you got it, g sub u. Similarly, what's multiplying d1 prime bar is also a bunch of numbers and s. Let's call this function of s, gd1. Well, those days, as you probably remember, are our transfer functions. We just finished our transfer function model for this very simple example. Yes,
what does S represent?
it's the Laplace transform variable. It doesn't have a physical meaning. There's no physical meaning. You can get some kind of interpretations in frequency response, but this is not limited to frequency response. Adam.
So if we had more than one disturbance, it just goes string of additions.
We'll do the general case in a minute. Okay?
So what is that? What did we just do?
We just got a model that doesn't have any x in it. It's a direct relationship between the Laplace transform of the measured output and the Laplace transform of the manipulated input, the one I'm designing, and of disturbances. It's an input-output model. It's in the Laplace domain. It's a dynamic, which means non-steady state input-output model. Felix.
So if you want to use that model, what are you going to substitute S for?
Nothing. You're never going to substitute S for anything. You're going to use this model to do some analysis, and then if you want to see what Y is doing, you have to go back to the time domain. You use the dictionary. Here's what we can do. All right. I was going to do something else first, but how can you use this model? Okay?
Yes.
To use this model, you would do first assume